Okay. One. Just give me one. I have to share my screen.
Yes, sir.
Can you see my screen, Darshan?
Yes, sir, I can see your screen.
Okay.
Yes.
So, thank you, Darshan and Kingshuk, for the introduction and the invitation to present at the Indian Institute of Technology Kanpur IEEE PS Student Branch Chapter event. I was there on sabbatical leave back in 2018 for about 5 months. Professor S.C. Srivastav and Professor Saika Chakravarti had invited me that time. So, as Darshan mentioned, the title of my presentation is on intelligent islanding. So, I have two parts of the presentation, or two separate works that we did. One is on transient stability prediction. That is, if some disturbances happen on the system, then whether the system is going to be stable or unstable, that is the transient stability prediction part. The second part is the controlled islanding. Obviously, if on a large system, right, if the generators are tripping and the loads are tripping, then the system the whole system may collapse. So we want to uh, do a controlled islanding if it is possible to do it, so that we can create islands where there is a generation load balance, so that we can retain as much of the system as possible. So this is the city here that I live in, Saskatoon. University of Saskatchewan is located in, Saskatoon. So we are on the banks of the South Saskatchewan River. It is similar to the Ganges, if you see in India, right? This is the campus here, about 1,300 acres. So this is a picture about 2 months before, until August, September time. And starting October, right, this is our fall time. And in another month, right, we'll have snow here. And it does become very cold starting December to about February and March. So this is my lab, the power system simulation lab. Typically, I have about 4 to 5 PhD students and about a similar number, about 5 to 6 master's thesis-based students. And then we also have project-based students as well in the group, 1 or 2 students. So here, this is the real-time digital simulator that I have. We have 2 racks, and that is for the electromagnetic simulations, the small time step simulations, and then we do the closed loop testing. I don't have any relays in this picture, but typically we use the manufacturer relays or the DSP boards, FPGA boards for closed loop testing, similar to what you have at IIT Kanpur, the Power Lab. So this is how I have organized my presentation. First, I will go through some of the basic definitions of system integrity protections schemes, SIPs, or it is also called as, in short, as system protection schemes, SPS, and remedial action schemes, RAS. That is also part of SIPs. SIPs was the original broad definition, and then the shorter form was SPS, and then the remedial action to prevent, say, for example, the cascading events on the system. The next one is going to be part 1, the transient stability prediction part. This was a work I did in collaboration with the GE Digital Energy in Markham. And the second part of the presentation is on the actual intelligent islanding. That is what is given in the title. That is the controlled islanding to prevent large-scale blackouts. So the basic SIPS definition, it comes from the IEEE C37.250. So this guide was around 2011, it was revised. And currently it is undergoing a further revision. So I'm part of the new working group, and that's how I have taken the definition from. Jeannie Henneberg is the chair of this working group. So SIP's basic definition, if you see, is it serves to enhance security and prevent propagation of disturbances for severe system emergencies caused by unacceptable operating conditions, and is used to stabilize the power system by taking control action to mitigate those system conditions. It encompasses system protection schemes, as I mentioned before. It also takes into account the remedial action schemes to correct whatever event has happened. And there are several other protection things that can operate, that is like under frequency, under voltage, or out of step protection schemes. I'll be discussing the out of step protection scheme in detail as part of SPS. So one thing I want to clarify is the out of step is one part of the system protection scheme. It is not the overall thing. For controlled islanding, the intelligent islanding that I'm doing. So out of step tripping, that is the generators, the synchronous generators, right? Or the loads, the synchronous motors. If they start slipping poles, we have to bring them offline. And we have to do it as quickly as possible. If we can predict it, it is good. And if there are some generator trips, we want to do islanding on the system. So the motivation for SIPS, again, it comes from the C37 guide. SIPS plays a vital role in power system reliability and resiliency. There was a joint IEEE SIGRE and EPRI global survey, which indicated the wide application of various types of SIPS. Before, if you see, right, the question that when I have earlier made this presentation, is it being used in practice? So the answer to that question is it is being used in limited way in Europe. It is also being used in US and Canada and different other parts of the world. So as the wide area of measurements, right, the PMUs started being widely used. So the SIPs are getting into the system. And as we move forward, right, we are going to see more of these SIPs-based schemes. So here from the C37 guide, the time of operation, if you see, right, I'm not going to go over all the blocks. Rotor angle instability, that is the out of step protection. So that is a transient instability condition for a generator. And the frequency instability. So if you see these things happen in the millisecond range. The wide area, that could be the wide area, it takes time to propagate. So it could be from several milliseconds to the order of seconds. And then the cascading events, right? Cascading is we are looking at a longer time horizon. So it could start from a few seconds to a few minutes. So the cascading event, which I'll be explaining in the second part of the presentation. So the common SIPs actions, right? There are various like generator rejection, load shedding. Say in an industrial plant, the under frequency load shedding, or the under voltage load shedding, then out of step tripping, angular stability advanced bonding scheme. The ones that are put on red, those are the ones I'm covering here. So if you look in this C37 guide, right, through the IEEE Explore, you can look into the various SIPs actions. So there are numerous in a SIPs, right, a combined system, there are going to be numerous things there. Now, when SIP's actions are implemented, we can do part of it, part of these actions, or it is not a mutually exclusive thing. It is an inclusive one. And to what extent we want to do it also, it plays a role. Because if we do all of this right, we may not be able to implement the entire SIP scheme. It becomes too complicated. So we may do it only in a limited way. The other thing that comes in terms of the reliability of the SIPs, it is the first important thing is dependability. When we design a SIPs, it has to operate when it is required to operate. The other component is the security. Do not operate when it is not intended. Okay, so when it is not intended to operate, we should not operate. And reliability covers both dependability and security. So reliability covers both. The overlapping region is the reliability portion. So the first part of the presentation, the transient stability prediction, I will start with some basics about the out-of-step protection. And then the work that I did with GE, right? I'm going to show the algorithm that we implemented based on the WAMP-based scheme. So on the right side, I have shown a two machine representation or two equivalent systems. So here the North American Reliability Corporation, it is divided into several, which includes US, Canada, and Mexico. So it is divided into different regions. Saskatchewan, if you see, right, and the Dakota region, they form part of the Midwest Reliability Organization. WECC is the Western Coordination Council. Then we have the Eastern Connection, and so on. So when a disturbance happens, right, here in a simple representation, I'm showing a two equivalent machine representation. So here the Saskatchewan region, it is shown as one lumped region, and the connection down south, right, is the other portion of the equivalent system. So that is represented as one large generator. So if some disturbance happens on the system, it could be either a stable swing, which is going to be fine, then at steady state, we'll recover back to our synchronous frequency, or it can be an unstable condition. So then the angle, right, it becomes 180 degrees. When the angle becomes 180 degrees, we start having the pole slips. So the way it works is in the North American region, if we have one pole slip, right, then we trip the generators. So obviously, at the instant when the pole slip happens, we cannot trip the breaker because there is going to be a very large restriking voltage that would be generated. So we wait for a favorable angle. We typically, after a pole slip, we wait for 270 to 360 degrees. So that is around the 0 to 90 degrees, plus minus 0 to 90 degrees. That is where we are going to open up the circuit breakers. Remember that this is not a operation of the circuit breaker for a fault. For a fault, the currents, the restriking voltage is going to be about 1.3 to 1.5 per unit. So if you have a 400 kV system, right, you can find the corresponding restriking voltage, 1.3 to 1.5 times per unit. But for a out-of-step condition, right, they are 180 degrees separated. So it is going to be 2 to 2.5 times. So for a 400 kV, it is going to be a RMS about 800 kilovolts minimum. So we cannot, having a circuit breaker for that large rating, right, is going to be very expensive. So that's why we wait for a favorable angle. So around 270 to 360 degrees, that is the North American practice. In Europe, about two pole slips are allowed. And the practice in Asia, depending on the vendor, it could be different. For example, I'm told for some of the hydro generators, right, in China, they allow up to 8 to 10 pole strips here, and the gas turbine generators. So here I'm showing the voltage across breakers. So for a short circuit breaking, right, it is 1.3 to 1.5 times the peak value. For loss of synchronism, you see it is 180 degrees separation, because that two machine representation that I was doing, right, equivalent system. So when a pole slip happens, so 180 degrees is going to correspond to this angle of separation between the two ends. So that's why we wait until this phasor, right, rotates, and between 270 to 360 degrees is when we do the separation, so that the restriking voltage is not very low. So this is the PMU locations, the NASP PMU locations 2021, which I got it from Wahid Madani. So if you see here, right, in the Canadian region, Alberta, British Columbia, and Manitoba, we have the PMUs. The Saskatchewan region, right, so far, the PMU, there are devices which have the PMU functionality, but they are not enabled still. So that's why we don't have those blue dots here. But the down south connections, right, there are PMUs. And as in the future years, obviously Saskatchewan has plans to enable these devices, and so too in Ontario also. So the synchro phasor based transient stability prediction, that is using the phasor measurement units, I'm going to explain you. This was a work which I did for G couple of years back. So this is one system. Here we are showing the optimal placement sites, the PMU location, so that the entire system is observable. Now, when a disturbance happens, the natural physics, what is going to happen is the system is initially going to separate into two coherent groups. So the coherent group B, which could be the large generator, the equivalent generator, that's why the angles are not becoming very large. And then the coherent group A, where the angle of separation is becoming large. So these are the two coherent groups. And this can be the real-time coherency determination. It can be there are now very good techniques to do the coherency. I'm not going to go over that in detail. The research is well established there. So if we want to do the prediction, right, what we are predicting is whether the angle is going to go through a zero crossing, then it is going to be a stable one. If the angle increases, right, say it becomes pi, 180 degrees, then the prediction says that it is going to become 180 degrees, then it is going to be unstable. And if we can predict in advance, right, we can then implement this SIP schemes I'm telling, or the remedial action schemes. So when we did this for a GE relay, the GE has an N60 relay, and we were looking at some enhancements to that stability protection. So what we do is, starting the default instance, we do the coherency detection, that is the red region here, and then we wait for about 20 samples. So 20 samples is when we are doing the for the forecasting. Okay, so we are creating a window of 20 samples, and then we have a buffer zone of another 10 samples. So overall 30 samples, and then we predict for the next 40 samples. And we have, and we'll check the stability for 3 consecutive windows, 40 samples, Then another window, we'll shift the window by one more sample and we'll do the prediction, and one more sample and we do the prediction. That's how we do typically in a relaying device. And for all three windows, if we are getting the same results right, then we can say for certain that the decision is going to be correct. So 30 samples are used for parameter estimation, like any adaptive filtering algorithm, and 3 consecutive predictions. If it says if it is going to become 180 degrees apart, system will be unstable. If it is going to be less than 0, then system will be stable. So the system level transient stability prediction here I'm showing for a system that we did. It was for a 9-bus system that we analyzed. So if you see here, right, the fault on the y-axis is the rotor angle and x-axis is the time. The fault instance was at 2.3090 seconds. So from here to the blue region here, 2.3920 seconds, we do the real-time coherency detection. And the prediction happens at 2.7, and the actual out-of-step conditions, if you see, right, they are happening at 2.9910 seconds. So the generated 2 pole strip, the actual pole strip is 2.94, but if with the prediction we are doing in advance. So if we predict in advance that the generator is going to slip pole, then we can take the remedial action before the actual the generator starts tripping poles. So we can prevent the generator from tripping. Similarly, you see here for the generator, 3 actual pole slipping happens at 3.1, whereas the prediction is at 2.7. So in advance. So this was the 9-bus system. For all generators, we put this GN60 relay, and we compared our results with the RTDS simulation, and then GN60 we had, and then based on our prediction algorithm, right, how it compared to the actual N60 relay prediction. So with the PMU models on the RTDS, we are using 12 cycles fault with a 12 cycles fault, which created an unstable condition on the system. With the virtual RTDS models we had, right, on the our prediction showed 0.283 seconds when we did the analysis using OpenPDC and MATLAB simulations, and the actual PMU, right, which is on the GN60 relay, which it gave 0.275 seconds. And for another fault on line 4-5, so the PMU model RTDS, it showed 0.375 seconds, and the actual PMU N60, it was 0.3749. So the first part was on the transient stability prediction using the WAMS-based scheme. Now, in this second piece of investigation that we did, it was with one of my graduate students now who works for PowerTech Labs in BC Hydro, Nipesh here. So here what we are looking at, an intelligent islanding scheme. That is, some generators are becoming unstable, then we want to do some line tripping, the out-of-step tripping on the lines, where to separate and when to separate. And we are looking at doing this one on a real-time basis so that we can prevent a large-scale blackout. Instead of that, if we can do a controlled separation, we want to minimize the number of generator trips and line trips. That was our goal. So it consisted of 2 parts, when to island and where to island. So the motivation for this work, it was back in around 2008 time that the islanding, right? That was after the 2003 blackout. So I was attending one of Arun Phadke's presentation. So that time they were talking of intelligent islanding would be, if it could be done, use in the with the future technology, that is going to be really helpful. So this is some of the points that were mentioned in the computer relaying for power systems, a textbook of Arun Phadke and James Thorpe. So I'm just going to give in quotes verbatim from the textbook. So islanding of the power system is a natural extension of the out-of-step detection function. The out-of-step detection that I was telling, right? Detection or prediction. For disturbances which are going to lead to instability between two coherent groups of generators, it is a logical step to separate the power system into islands, which contain each coherent group of generator and some load. Wide area measurements available at the system control center. That is, right now, if you see, right, the measurements are there, and we can see whether the system is going to become stable or unstable. But the closed loop, only few utilities have implemented, or few regions have implemented on a small scale, but future we'll have more of those. So wide area measurements available at the system control center will help identify desired boundaries of separation depending on which generators have formed a coherent group, and what loads and generation within the islands to be formed would be controllable to the desired extent. So usually this requires out-of-step blocking at undesirable points of separation. One thing to note here is we are not going to trip wherever possible on the lines. Some regions tripping, out-of-step tripping may not be desirable. So in those regions, we are going to implement the blocking function, even though it may take a larger portion of the system out. And in some portions, we'll do an out-of-step tripping at desired locations to form the islands. So that was after the 2003 blackout, right? In the Swiss region, there was another blackout just following the August 2003 blackout. It was just a couple of months after that. So what had happened is, because of this out-of-step tripping, right, happening, actually a major portion of the Swiss system went down. So cascading outage, that is another thing when we are, say, a blackout phenomena, right, or a blackout scenario. To do those scenarios, what we would need is some real-time simulations and creating the events that would create a cascading outage. Typically, these are the this 4-step process. This is how we did it. We had a precondition system operating within constraints, and then an initial event. We created an event on the system, like a short circuit, overload, loss of generation on the system, that that became this second stage. Third is creating this cascading event. That is, the lines, say if some line tripped, right, the other lines will overload, they are going to trip. And then some relays may also misoperate due to out-of-step condition. So that is another possible event. And the fourth is the uncontrolled islanding and taking a larger portion of the system off. So the intelligent islanding as a research and an implementation, if we do this one right, it has to be done first of all in online fashion, and then if we can use some machine learning algorithms, right, to handle the complex scenario, then we can do it in a quick fashion and in a more reliable fashion. So the power system here is split power system into international islands, there are two parts to it. When to island, when do we start islanding, and where to island. That is, in what portions of the network we want to do the out of step tripping. And there would be some portions of the system where we don't want to do the tripping. So for that part, right, in the research that I did with a grad student, we were looking at a machine learning based algorithm, the spectral clustering. So in the when to island, right, when we looked into the literature, like what Arun Fadke and James Thorpe had proposed was a wide area measurement based scheme. Then in terms of the actual implementation or in a realistic way, when we looked at it, then we started thinking, do we need to do everything as a wide area measurement based scheme, or we can do it in conjunction with some of the relay operations that would happen on the system as a local protection. So the typical way that it happens in protection, right? The protective relays on the lines and the generators, they act based on the local available data. So the way we looked into the problem is, we looked into it as think locally, that is, the relays are going to operate based on the local conditions and act in a global fashion. That is for the intelligent controlled islanding part. The second part is in the global fashion. So here is the diagram that we had here. I'm showing a 4-generator system. So the generators, right, I'm showing it for the generators. The same thing could be done for the lines. In this particular implementation, or in the diagram, I'm not showing for the lines, but the communication, right? So for the generator protection, say if some generator is going to go out of step, that status could become communicated to the central when decision unit. Okay. So instead of a WAM space scheme, right, instead of sending the data, all streaming data, what we are communicating is just the status of the relay, whether it is stable or unstable, the out of step relay. So these lines, okay. For the coherency detection part, we still we are using the PMU based measurements for the real-time coherency detection. The reason we still continued with the PMU measurements was the coherency methodology that we saw in the recent literature, right? Using the PMUs, it was a very reliable technique, so we went with the coherency detection in a real-time basis with PMUs. Now here, this is for the 9-bus system. So we have 3 generators, G1, G2, and G3 located at bus number 1. G1 is at bus number 1, G2 is at bus number 2, and G3 is bus number 3. Now, on the right side figure, right, I'm showing a graph representation of the system. The nodes indicate the bus number, and the lines, right, it indicates the power flow. So between line 1 and 4, the power that is flowing is 71 megawatts. Okay. Similarly, between 5 and 4, it is 41. 4 and 6 is 30. Okay. So on the top graph here, right, after a disturbance window, the observation window is where we do the analysis. So as I told you, right, after an initial major disturbance event, the natural split that happens is into 2 coherent groups. Multiple groups only happen at a later time instance. So the first piece of analysis we do, right, for stability is based on 2 coherent groups. So this is the observation window here. Okay. So these things, they are all following similar patterns. So this is one coherent group, and these generators out here, right? So these two swings, they are together, and these two swings, but the pattern, if you see, they are going together. Okay. They may further split later on, but the initial, for the initial split, right, it is two groups here. So coherent group 1 here, coherent group 2. So here is the flow chart, identification of coherent generator groups. We convert the power system into a graph. And this original graph, right, we do a graph reduction using spectral clustering, which I'll show it to you on the next slide. And then once we do the clustering, right, then we can see where to split. Okay? And the original cut set recovery, that is the which lines to do the out of step tripping. So here in this diagram, right, graph reduction, we'll have the must-link constraints. Say the generator, right, when it is connected to a transmission line, so we have to supply that power, right? So we are not going to disconnect for that portion of the network. So those two nodes could be lumped together. So the transmission line availability constraints and the generator coherency constraint. For example, bus number 2 and 7, they are clubbed together, and 1 and 4. Okay. So I will go back to the previous slide and show you. 2 and 7, right? G2 supplies the power through, there is only one line. So these two, we should not trip here on this line, okay? So 2 and 7 is a coherent group here. And similarly, 1 and 4 is a coherent group, and 3 and 9 is a coherent group, okay? So 2 and 7 is a coherent group, 1 and 4 and 9 and 3. So that is one reduction. The other one is based on the split, right? That so the nodes here, they form one coherent group, and so 2 and bus number 5, right? They form one coherent group, so they are on the spectral clustering, right? This is 2 and 5 together, and 1 and 6, they form the other group. So where we are going to separate is through these portions of the line, 61 and 41. So 61 and 41, this is the place where we'll do the out of step tripping. So we'll have out of step relays on these portions of the line, and then we'll separate these two if a disturbance happens, right? Major disturbance, and because they are splitting as two coherent groups, so the out of step relays are going to create an island. So this is going to be one island, and this is going to be other island. So this is why I chose the 9-bus system. So in terms of a schematic, right, it was easier to show it to you. We did the actual analysis on the IEEE 39-bus system, the New England system that in the United States part, the equivalent network, that is where we did the analysis. So this is the New England system. So the next one is the cascading outage simulation, how we did the cascading outage. So what we did is we implemented the line overload limits for each lines. We had the governor, PSS, AVR action for all the generators included, okay, and the line overload trips and the generator out of step protection. We did not implement the motor protection, the motor over voltage and the under voltage protection, but those could be included as well, and we can do the simulations in more detail. Okay, the main concept is what I'm explaining here. So the initial event, we created a 4 cycles fault on line number T27. So it is carrying 603 megawatts. We did implemented a 4 cycles fault. So what happened is because of this line trip, because a fault has happened, this line is obviously going to trip. So once T27 tripped, what happened? Line number T28 got overloaded. From 42 megawatts, it went to 550 to 650 megawatts. The power flow increased from the original value, 42 megawatts, it increased to 550 to 650 megawatts. So T28, because of the overload condition, T28 line tripped at 1.659 seconds. So once T28 tripped, then you see line T19 here, it got overloaded. T19 got overloaded and T19 tripped at 1.8006 seconds. Okay. So followed by this, we had the generator out of step functionality for G7 for all the generators. So what happened is G7, the out of step relay, because it started slipping poles, so it tripped at 1.8558 seconds. So you can see the cascading one event after other, right? The power equipment, they are tripping. Okay. So this was for the G7, right? We had, I'm showing it based on the two double blinder scheme. So fault applied at 0.8 seconds, it went here. Fault cleared at 0.867 seconds. So it encroached into the, it came out after the fault cleared and then it came inside. That's why the out of step relay is tripping for G7. And then followed by that 4, 5, then line number T6 got overloaded. So T6 line is now tripping at 1.9804 seconds. And then followed by T26 trip at 2.0304 seconds. So followed by that G4 and G5, they tripped on the overload condition. Okay. At 2.0594 seconds and 2.1018 seconds. So the gray area is the one that is finally this whole region, right, got blacked out. Okay. So starting with the original T27 fault at 0.8 second, these are the sequence of events, and at 2.108 seconds, right, this is the island one that is grayed area. Rest of the system is intact. So creating such a scenario, right, it is not very easy. We have to do various hit and trial and then implementing these overload conditions and all. So to create this kind of a cascading event scenario. This is the other one, the unintentional island for a T21 fault. So again, starting at 0.8 seconds. And these are the two regions, right? That all, the gray area you see here, those are the ones that where the unintentional island or losing all the generation here. Okay. So you can see 1, 2, 3, 4, 5, and 6 generators are lost. Okay. The island 3 is still intact. The rest of the island 1 and 2 are the ones that are blacked out. And this is based on a simulation, real-time simulation, but in an actual scenario also, it don't take very long. It is in the order of seconds, right? That is an unintentional island happening. For example, the 2003 blackout, from the time instant when the SCADA systems showed, right, the whole event within 60 seconds, the eastern region of United States and Canada, right, the Ontario and Ontario region, they got blacked out in a matter of 60 seconds. So where to island? So this is the original graph representation of it. Then the graph reduction, okay, based on the simulation, implementing that code in online, and then the spectral clustering, right? The system separating to two regions. So this is one region and this is the other region. So once we have the graph reduction and then we have the spectral clustering done, right, then we can see where to separate. Okay, so we can have these out of step relays located in these areas here, T23 and T24, to do a controlled islanding or an intelligent islanding. So on the top figure, right, the first one, the A figure corresponds to the one which is for unintentional islanding. If we don't do anything on the system, we just have out of step relays for generators and the lines, then this is the region, right, that got blacked out. And if we did a controlled islanding, right, we are saving all this portion of the system. This only small portion is the one that is we are losing it. And in the bottom two figures, right, I'm showing you without controlled islanding, the actual generated pole sweeps, okay. G6 at lost at 1.659, G7 lost at 1.8, G4 and G5 lost at 2.1. So that is the unintentional islanding. So all these generators are lost with G4, G5, G6 and G7 plus the lines. Now with the controlled islanding, right, it is the initial fault is 0.8. The controlled islanding is triggered at 1.2956 seconds. So G4 and G5, they trip. Okay. Sorry, the generators that trip are G6 and G7 with the controlled islanding. G6 and G7 are the ones we are losing it here. Whereas G4 and G5, right, they are still intact. Okay. G4 and G5. Whereas you see with the unintentional island, G4 and G5 also were gone. So between the unintentional island and the controlled islanding, right, we have 0.8062 seconds. In matter of 0.8062 seconds, that is the time span, right, we have. So we are able to do the controlled islanding in advance. By doing that, we are saving the generators G4 and G5. I have another scenario. Just before going to the second scenario, in terms of the number of components lost, if you see for the unintentional island, so G4, G5, G6, and G7, so 4 generators lost, 30%, 8% of the capacity is lost. The loads that are lost are located at bus 15, 16, 18, 20, 21, 23, 24. So it is 7 loads lost, 37% capacity. And the transmission lines, right? Again, 11 transmission lines lost and 34% of the capacity. Whereas with the controlled islanding, you see we lose only G6 and G7, two generators. The capacity lost is 20%. The loads lost is 3 versus 7 for the unintentional islandings. And transmission loss, lines lost is 5 for with controlled islanding, whereas with an unintentional island, it is 11. This is another scenario we had here. So these were the two unintentional islands, but with a controlled islanding, right? Then we have a smaller region. So this is the unintentional island. The instance of generators being lost is shown here. G7 followed by G6, G4, G5, G3, and G2. Okay. So the unintentional island is happening at 3.488 seconds. And with a controlled islanding, it is triggered at 1.3005 seconds. So it is 0.21875 seconds before an actual full-scale blackout. So with a SIP scheme, 0.218 seconds, or in the previous scenario, we had 0.806 seconds, right? That is the time horizon where a remedial action scheme is being implemented, that is closing the loop. So in summary, what were the advantages of this intentional islanding we did? The first thing was it did not depend on the system configuration and generator inertia. If you see the classical textbooks, right, we use the equal area criterion for transient stability analysis. We have the M term. So we need the inertia of the generators. And we would need the current operating state of the system, which generators are in service and so on, to find the inertia of the system. And finding the overall inertia of the system, right, accurately, it is not an easy task. We would have to have the full-scale PMU measurements to find the inertia. Here, when we did the implementation, right, it did not depend on the generator inertia factor. So that was one key advantage. And it also did not depend on the system configuration. So system configuration here is the network topology. What I'm talking means it could be implemented on another network topology also. But in terms of the protection, right, there are many other, as I listed for the SIPs, there are so many protection functions. We implemented some of them, we did not implement all of them, but that is something that can be done on the system to do a very realistic analysis. The second key advantage of our algorithm was think locally and act globally. So that's how a protection and control operates. So the use of local generator out-of-step protection, it was the think local action. And it also simplified the communication to the central control room. We are only communicating the zeros and ones. So we implemented it using the 61850, the routable goose, the substation-based routable goose that is available now. Recently, it has become part of the standards. So we implemented using the routable goose so that it simplifies the communication for the closed loop control. We predicted system-wide instability 0.8062 seconds and 2.187 seconds for the two scenarios before an actual unintentional island. So for a RAS, this is 0.8 in terms of a computer hardware, right? This is quite a bit of time to do the processing on an actual RAS on a device. And we could save safe significant number of components, and the region of blackout. So thank you, everyone. So this concludes my presentation.
Thank you, sir, for sharing your rich experience in the domain of transient stability prediction, out-of-step protection, synchrophrasor-based transient stability prediction, and giving us a overview of SIPS. I'm sure that all our participants must have gained an insight into the topics. Now I will start with the question and answer session. We have few queries in the chat box.
We already see there are quite a few questions.
Yes, yes.
Yeah,
So,
yeah.
okay, the first question is from Mr. Ravi. He is asking what if prediction value does not go above 180 degree or 0 degree and lies between 0 degree and 180 degree.
If it lies between 0 to 180 degrees, right, it is going to be a stable condition. Just look at that equal area criterion condition. So it is, say, if the initial angle is 130 degrees, right? The generator, say, single machine infinite bus representation. If the generator is operating at 30 degrees, so a disturbance happens, and before 150 degrees, right? If the accelerating area and the decelerating area become equal, then the system will become will evolve into a stable condition. So that is a stable condition, right? Ravi, does it answer your question?
Yes, sir. Yes. Is it audible? My voice?
Yes,
Yes,
sir.
yes, yeah, it is great.
Yes, sir. Sir, actually, when we draw the diagram, power angle curve, usually we tell that whenever the angle goes the 180 minus delta. So we have 2 points where we can achieve the load generation balance, delta and 180 minus delta. So it may go above 180 minus delta sometimes, and which is less than 180 still. So in textbooks, we tell that if it crosses 180 minus delta, it would be a unstable point. That's why we do not consider that point as a stable operating point.
Okay, your point is that so once it crosses 180 minus delta, right? If the accelerating and the decelerating don't become equal there, now again the acceleration has set in. It will go into 180 degrees. After 180 minus delta, it starts slipping poles.
Okay.
It is not going to just stay there. You see in the curve, right? You plot electrical power versus delta. You will see that after that, right, again the acceleration has set in. So you can never make the acceleration equal to deceleration.
Okay. Thanks.
Okay, we have another question from Sunil. Sir, what will be the effect of correction measure on the system operation during during false prediction?
During false prediction, it can happen in a boundary condition, right? The way it works in protection is, I will try to answer that one in more in terms of out of step prediction or detection. If in a boundary condition, right, if we predict it as an unstable scenario as a stable condition, that is problematic. But if a system that is means marginally stable, if we predict it as unstable, that is all right. The problem is an unstable condition. If we predict as stable, that is a problem. Okay. So what will be the effect of correction measure on the system operation during a false prediction? So it can happen for a boundary condition. So as long as it is a marginally stable case, say like the earlier question Ravi asked, right? The acceleration and the deceleration area, say 180 minus delta, say around 150 degrees. If it doesn't become equal until 149 degrees, right? Then because of error, measurement errors, we may predict it as unstable. That is all right. But if we predict it as stable, then it will be a problem. So we have to have an adequate margin. So to prevent this false prediction. Sunil. Does it answer your question?
Sunil, you can respond.
Yes, sir. Thank you, sir.
Okay, another question is from Jitendra. What will be the effect of large penetration of RER on transient stability prediction?
What will be the effect of large penetration of renewable energy? That's a very good question. When we have these wind resources and all, when the penetration levels were small, they were all lumped together. When we have large penetration of renewable energy resources, right, then again we have to, in terms of out of step prediction or the out of step tripping, right, there are those equivalenting analysis that are being done in terms of combining these synchronous and the asynchronous sources. There are various ways of looking at it. The one way we did the analysis was, we did the analysis using the equal area criterion in the time domain. We converted everything into the time domain and we did the analysis using the equal area criterion. Recently, there have been a couple of publications there. There are models available for this representing the synchronous and the asynchronous type of renewable energy resources. So we would have to have a very good model available for the equivalenting. So
Thank you, sir.
renewable energy resources, they are going to affect our out of step prediction. That is true.
We have
So I
another.
don't have a concrete answer, Jitendra. That is an ongoing work. There are some recent works. The way we did it is we represented still it is an AC system, it is a synchronous system. So we at select points on the system, we are doing the equal area representation in the time domain. And we do the accelerating and the decelerating for small increments, we calculate it. If the accelerating and the decelerating areas become equal, then it is stable, otherwise it becomes unstable. Because we do it in the time domain, right? We can do it as a local out of step protection on a line or on a generator.
Sir, so for to plot this characteristic on the equal area criteria, so do we need to model all the renewable energy resources like a synchronous resonator model, and then we have to plot all these characteristic on as a equal area criteria, right?
No, we don't have to represent them as synchronous generators. We'll be representing them as they exist, as a wind or a solar PV. So on select portions of the line, right, where we want to analyze this out of step condition, that is where, based on the local voltage and current measurement, what I'm doing is finding out the active power flow on the line. So a disturbance happens. So so at the trigger point, right, what was the power flowing on the line? And as soon as a disturbance happens, the electrical power is going to go down. Okay. So that becomes the accelerating area. and after some time, right, as a swing, it would become as a decelerating area. So in increments with respect to time, I calculate that.
Okay, sir. Thank you, sir.
Jitendra, what I will suggest is there is a paper I published in 2010, the equal area criterion in the time domain. So if you in IEEE power delivery, so you can take a look at that work.
Sure, sir.
And also in terms of dynamic models, I recently in the last 2 years, there have been a couple of very good publications that have come representing both synchronous and the asynchronous type, the wind farms, and to do a dynamic model representation to do the analysis. And what the authors are claiming is this is going to be a good model to do this kind of an analysis for the stability.
Thank you, sir.
Without resorting to a full-fledged EMT model of all the various types of generator.
Okay, we have another question from Mr. Ravi. Sir, does finding coherent groups before disturbance occurs possible as you did in 9-bus system, because mainly coherency depends on initial conditions?
No, it is not before the disturbance. What I'm saying, that was a real time, based on the PMU measurements, right? After a fault event happened, how those generators are splitting, monitoring those angles, right? At the various buses, that's how I'm showing that the coherent groups.
Okay, okay, sir. So that's you're doing on real time.
Yeah, real time. But your question, right?
Yes, sir.
This reminds of a, if you see the SIP schemes and the remedial action schemes, 90% of those schemes are done as a planning.
Okay.
In the planning department. So the planning department has those simulation models. They will create those events at different portions of the network, and before in hand, they already know that if some events happen on those portions at different places on the network, how the system is going to split. So they already have those information available for the operators.
Okay. Sir, but one coherent group of generators, they may act differently for different initial conditions, because it
Yes,
depends on nature of the disturbance and also the initial condition. So for the same type of disturbance, if the initial conditions are different, then the coherent group that may not be coherent again.
yes, that is possible, but those scenarios, right, depending
Okay,
on
so-
the loads and all those, that's why those planning department, right, they have a lot of historical data. They create those for those events for numerous studies, right? They put it in a loop. They create those false scenarios for different locations, and they run those files, right?
Okay, okay.
If it is done on a offline, like some software like PSSC, here
Okay.
that is one software that is widely used, that Siemens PTI1. That's why it takes sometimes couple of days or weeks to run all those scenarios.
Okay.
That is where this RTDS real-time simulations became very handy, right?
Yes, sir.
When they were developed in late 80s, 90s.
Yeah.
They wanted to save the time for the planning engineers. Real-time simulation means 10 seconds of simulation will take 10 seconds, right?
Yes, sir. Yes.
And you would have heard this KEPCO system, right? The South Koreans, the entire Korean Power Corporation, their whole system is on RTDS.
Okay.
They are using some 27. It was in the late 90s or early between 2000 to 2010. So that was why they put the whole system on RTDS is they will key in that operating scenarios and the possible, the credible contingencies they create, and they want to see how the system is going to evolve in terms of transient stability, the line overloads, and so on. The reason why they did put their entire system on RTDS, right, was to do this kind of analysis quickly for the planning department.
Okay.
And I can tell you one more. And now the Southern California Edison here, the last I heard, that is the largest RTDS rack implementation. They also have their entire system on RTDS.
Okay, sir.
And Hitachi, from Hitachi, I heard one very interesting thing. It was on the Japanese system. This is an implementation dating back to about 10 years back. What had happened was between one of the interconnections, right? It was, no, I don't remember the full system details. It was a 400 kV system, and they wanted to transmit, there was going to be more generation available in that region. So they wanted to transmit more power, but to add one more additional line, right?
Okay.
The regulatory bodies, because Japan is very densely populated, right? They ruled it out for that 400 kV system. They did not get a right of way. So so building another line was not possible. So what they did is they put the simulations for this interconnection on an RTDS, and they run it on real time based on that operating scenario. And they look at the line overload limits and all. And based on that, they do the power transfer on those lines. So,
Okay.
so they could avoid actually building a line. And it was around 2015, the Hitachi engineers told that they did not have a single event misoperation. So they are having the RTDS simulations going in real time for those operating scenarios, and they are doing the power transfer based on those instead of the static limits on the line. They are doing the dynamic line limits.
Okay. Sir, another question in the chat box that I have. So as you said that controlled islanding and uncontrolled islanding, so that we can see whether it is a controlled or uncontrolled, in the air, in their own islands, both loads and generators are met. Means generational load balance is still there in their own islands. So in terms of load and generation balance, how does the controlled islanding would be beneficial?
Now, the controlled islanding is in terms of the limiting the region of blackout. Now, once we do the islanding, right, then we have obviously we have to do a generation load balance. Otherwise, you are going to have if the generation is surplus, then we are going to have an over frequency condition. Or if the load is more, right, we would have to do the load shedding to again restore the frequency within that region.
Okay, thank you.
So locally, we would have to do the additional things on the system.
Okay.
And that's a very good point. If you only certain portions of from the computer relaying text, right, I put in verbatim, but there were in between that points also mentioned there. If you look in Fudke and Thoughts text.
Okay.
So within that system, we would have to do the local protection as well. Okay, and this frequency stability, the over voltage, under voltage, those things also have to be met.
Okay. Thank you, sir. Thank you. It's a great presentation.
You're welcome. Thank you.
We have another question from Subham. How fall right through capability of renewable energy sources will affect islanding?
It will be beneficial. The fault right through, right? The controlled islanding or the generators that are going to go out of step, or the those things instead of happening right away, it will take much longer. So controlled islanding, it is going to be beneficial. We have more time available to do this. The fault right through capability, right? Fault right through, what is there is the RES is not going to disconnect. It is going to ride through it, right? So that generation would be available for a longer period of time.
So we have last question from Mr. Atul Soni. During the island formation, do the overcurrent relays need to change their setting to maintain coordination, or is it already considered?
Overcurrent relays, no, we did not change their settings. They were whatever overcurrent relays we had, the original settings we had. And here, this is a transmission system. So in terms of the loading we are implementing, and the protection, that is what we have is the distance protection on the line, not overcurrent. If it is a distribution system, right, then we can have the overcurrent type of protection. So on a active islanding, the terminology, the islanding is very common with the renewable base, or on the distribution systems as well. With say a distribution system connected to the grid, if a grid side fault happens, right, we do an active islanding separator, because if we have renewable energy sources, right, within the distribution system, we want to supply power through this distributed energy resources. That's why we do active islanding. There you can have overcurrent type of
Okay, I think there are no any further queries. Thank you, sir, for such a wonderful presentation. And I hope that all our participants must have been really benefited from this. So on behalf of IEEE PES SBC at IIT Kanpur, I would like to present a small token of appreciation for being a research person in PERA 2022. So please accept our token of appreciation.
Thank you. Yes, definitely.
We hope to meet you in future editions of PERA as well. And
sure. And I see Vineet, I saw him during the PS general meeting. He was also there.
Thank you so much, sir.
Yeah, thank you.
Okay, we will start our next session at 6:30 p.m. today, and it will be by Professor Traptijan from IIT Indore. I hope we will have all of you together in that session, and have a nice day. Thank you.
Thank you, Darshan.